In standard Langlands theory, ramified representations often generate chaotic volume fractions and infinite dimensional crosstalk. But by applying BSSZ in low expansion bounds, we can force that complexity to resolve into a single exact integer. To reach this result, we evaluate the local ramified Hecke operator, UP, over the Iwahori fixed basis of a GL3 matrix. The diagonal contains our torus characters, alpha 1, 2, and 3. Above them sit the unipotent blocks, which register the arithmetic crosstalk. This red upper triangular crosstalk is the primary source of entropy in the matrix. To calculate a clean trace, we have to trap and neutralize these specific entries. If we map these entries to their arithmetic source, the simple roots x and y come from the set A, but the top cell entry z is the result of their interaction, belonging to the set AA plus A. Here, we apply the Minkowski polynomial bound. This strictly contains the quadratic set to the size of a to the power of 2 minus c. Because of this inequality, the matrix entries are structurally trapped. They cannot undergo maximal expansion as the complexity of the data increases. By forcing the arithmetic sets to obey these combinatorial boundaries, we create a mathematical ceiling that prevents infinite leakage when we reduce the matrix. We move toward the reduction by routing the matrix through the Jacquet module functor. This mods out the unipotent translations MA of n from the representation space. In a standard ramified representation, this reduction step would be highly lossy, but since our crosstalk entries are constrained by the Minkowski bounds, they are unable to escape the unipotent domain. The functor maps those confined elements to 0, leaving behind a strictly diagonalized matrix of torus characters. The Jacquet functor removes the non-commutative components of the matrix, leaving us with a decoupled system. To evaluate the trace unitarily, we rescale the diagonal by the modulus character. This follows the BSSZ law, where Tj is proportional to p to the negative 3 minus 2j over 2. Pause the video. Calculate the powers of p for indices 1, 2, and 3 to fill the scaling matrix. For j equals 1, the result is p to the negative 1/2. For j equals 2, it's 1. And for j equals 3, it's p to the positive 1/2. This constructs the required scaling matrix. We multiply our diagonalized matrix by the scaling factor, merging them into a single, fully decoupled torus matrix. This synchronizes the scale geometry across the diagonal, ensuring that the trace will not be distorted by the volume of the local field. With the matrix normalized, calculating the trace becomes a simple addition down the diagonal. As we sum the characters, the internal p-adic scaling factors balance out. The trace resolves to the exact integer dimension of the group, SME. This integer result is possible because the BSSZ constraints neutralize the fractional volumetrics that usually govern ramified traces. Because this trace matches the group rank, the local Hecke algebra aligns with the global Galois deformation ring. This alignment ensures the Taylor-Wiles patching rings remain flat, preventing geometric matrix shearing as we climb infinite towers of field extensions. To recap, we start by taming the inputs, applying combinatorial boundaries to the matrix entries. Second, we use the Jacquet functor to mod out unipotent elements and diagonalize the system. Third, we apply unitary scaling to balance the diagonal against the modulus character. Finally, we take the trace. Following this pipeline collapses the complex topology of the module into a stable integer identity. Grab a screenshot of the steps and we'll see you in the next lesson.